And the most important part of this lesson is to introduce our optimization algorithm. Since the mountain railway alignment design is a very complex problem that's nearly impossible to be solved directly using just one method, thus we constructed a two-stage strategy for this problem. The first stage of this strategy is to find possible railway corridors in the board study area using a distance transform algorithm. That is by searching permanent passes, three-dimensional passes, using the distance transform, and then use this path as the center line to generate a three-dimensional railway corridor. This is the area to corridor stage. Then, as a corridor to alignment stage, we found the detailed alignment solutions in this narrowed corridor using the genetic algorithm. This by using the improved genetic algorithm, the detailed alignment solutions, including the geometric configurations, the railway locations, and the construction complements, can be found in the corridor. This is the math flow of this method. I don't want to talk about this figure in this lesson, and you can study this by yourself after the class. In the first stage, that is the area to corridor stage, the distance transform algorithm is used. Some basic conceptions about this method is that to propagate local distances and local passes and to generate the global distance and the global best path. This method requires a neighboring mask. That is the neighboring mask. And each element in this mask include the Euclidean distance from this cell to the center cell. The whole metric can be divided into two parts, the upper left part and the lower right part. And these are used respectively for the forward scan and backward scan processes. Firstly, the distance of each cell in the study area. The study area is represented by using a lattice. The distance of each cell is firstly initialized. The cell containing the start and the end point are initialized with 0, and other cells are initialized as infinite. Then a two-pass scan of this lattice is conducted from the top left to the bottom right, and then from the top right to the bottom left. For example, look at the right picture. In this figure, it shows the global path generation process. By using a neighboring mask, the distance between the central cell and the boundary cell can be calculated and can then be propagated by scanning all the cells line by line until the target point is reached. Then the best path, that is the lowest cost path, can be generated by tracing the best local path and the lowest local distances to generate the best path. The advantage of this method is that it can find many promising paths satisfying multiple complex constraints. The disadvantages is that the resulting paths are piecewise linear rather than smooth curves. As we know, the railways include tangents and curves, However, this generated passes are polylength. Thus, this path must be refined into final alignments. In this process, the alignments inevitably deviate from the optimized passes.